Welcome back to Mr. Vaughn's Classroom. Please take a moment to hit that subscribe button, leave a comment, and give this video a thumbs up. Today, we're looking at Unit 5, Introduction to Exponential Functions, Lesson 5, Representing Exponential Decay. Our learning goal today is to think about how to show and talk about exponential decay. We have 3 learning targets. As we work through the practice problems, keep these 3 learning targets in mind. Number 1, I can explain the meanings of A and B in an equation that represents exponential decay and is written as y equals a times b to the power of x. In this form, a is going to be our initial amount, b is going to be the growth factor, that's the number we're multiplying by each time, and x will be our input that tells us how many times we're going to multiply by that growth factor. Number 2, I can find a growth factor from a graph and write an equation to represent exponential decay. To do this, we're going to take the second y value, divide it by the first y value, and that will give us the growth factor. Then to write an equation that represents exponential decay, we're going to write it in the format you saw in Learning Target 1, where y equals the initial amount times the growth factor to the power of the input. And Learning Target number 3, I can graph equations that represent quantities that change by a growth factor between 0 and 1. So you need to know how to take the initial amount and then multiply it by the growth factor repeatedly, plotting each point in order to create that graph. For glossary terms, we have growth factor. In an exponential function, the output is multiplied by the same factor every time the input increases by 1. The multiplier is called the growth factor. Now we can begin the practice problems for Unit 5, Lesson 5. A population P of migrating butterflies satisfies the equation P equals 100,000 times 4/5 to the power of W, where W is the number of weeks since they began their migration. Number 1 wants us to complete the table with the population after different numbers of weeks. So, this is that A times B to the power of X format that they were talking about in the learning targets. This number that's by itself is the initial amount. And then this number that has the exponent is going to be the growth factor that we multiply by each time. So if the initial population is 100,000, then 0 weeks after they started, our amount would be 100,000. Now what we're going to do is each week we're going to multiply the remaining population by the 4/5 of the population that remains. 4/5 is equal to 0.8. So we have 100,000 times 0.8, and we get 80,000. Now we're going to take that 80,000 and we're going to multiply it by 4/5, which is 0.8. And that leaves us with 64,000 butterflies. Now we're going to take those 64,000 butterflies that are remaining, and we're going to multiply them by 4/5, which is equal to 0.8. And that gives us 51,200 butterflies. And finally, we're going to take those 51,200 butterflies that are remaining, and we're going to multiply them by 4/5, which is equal to 0.8. And that gives us a population of 40,960. Number 2 wants us to graph the butterfly population. Our input was the number of weeks. So I'm going to label it weeks, and I'm going to label it increasing by 1 each time. That means our output was the population. And it needs to go up to 100,000, so that's how I'm going to label it. Increasing by 10,000 every line. I'm labeling every other line just to save time. And that makes the top 100,000. Now, when we started, we had a population of 100,000. A week later, we were down to 80,000. After 2 weeks, we were down to 64,000. After 3 weeks, we were down to 51,200. And after 4 weeks, we were down to 40,960. So this is how we would graph this function. Number 3. What is the vertical intercept of the graph? We see the vertical intercept right here at 0 weeks, 100,000. What does it tell us about the butterfly population? It tells us the initial population was 100,000. And number 4, about when does the butterfly population reach 50,000? We can see that we are slightly above 50,000 at 3 weeks, and we're well below it at 4. So, shortly after 3 weeks, the population reaches 50,000. And one last thing we should do, because we do have time between the weeks, and because we do have population declining throughout the weeks, we should go ahead and connect all these points with a line, because every point on this line would also make this function true. If you have any question about how to solve this practice problem, please leave a comment below and I'll get back to you with any assistance I can offer. Our next practice problem says the graph shows the amount of a chemical in a water sample. It is decreasing exponentially. Find the coordinates of the points labeled A, B, and C. Explain your reasoning. So I talked about this in the very beginning when I was explaining one of the learning targets. If we have the graph and we have 2 points here labeled for us, to find the growth factor, take the second y and divide it by the first y. So in this case, my second y is 800, and my first y is 1,000. And we can simplify this by dividing the top and the bottom by 200. 800 divided by 200 is 4, and 1,000 divided by 200 is 5. So the growth factor is 4/5. Now, if I want to find point A, then point A is going to equal the 800 that we have on our second point times 4/5. So we can pull up a calculator. 800 times 4/5 is equal to 0.8. And that's going to give us 640. So the actual point, because x is increasing 1 each time, the point would now be 640. If we want to find point B, we're going to take that y value of 640 and we're going to multiply it by that growth factor of 4/5. Again, 4/5 is equal to 0.8. And that becomes 512. And the coordinate for the point, we can see that the x value is 3, and we just calculated the y value as being 512. And finally, if we want to calculate C, we're going to take that Y value from point B, which was 512, and we're going to multiply that by 4 over 5. We'll go into the calculator. 512 times 4 over 5 is equal to 0.8. And our final result is 409.6. So the coordinate for the point, we can see that the x value is 4. And then we just calculated the y value to be 409.6. If you have any questions about how to use a graph to find the growth factor and then use that growth factor to find the value of points, please leave a comment below and I'll offer any assistance that you might need. Our next practice problem says the graph shows the amount of a chemical in a water sample at different times after it was first measured. Select all statements that are true. So here's an example of why you want to read all of your answers first. Because if you do, then what you'll notice is that choices A, B, and C all go together, and only one of them could be true. So if we look at A, it says the amount of the chemical in the water sample is decreasing exponentially. B says the amount of the chemical in the water sample is not decreasing exponentially. And C says that it's not possible to tell for certain whether or not the amount of the chemical is decreasing exponentially. And if you looked at it and you tried to guess, then you could say that it appears to go from 2,000 down to 1,000, down to 500, then down to 250, down to 125, down to 62.5. So it does appear to be multiplying by 1/2 each time. But the problem is you're guessing. That second dot might be at 1,000, but it could also be at 975. We just don't know for sure because it's not actually labeled and it's not directly on a line that is labeled. So for that reason, C would be correct. Not possible to tell for certain. So that means A and B are wrong. Now we look at D. When it was first measured, there were 2,000 milligrams of the chemical in the water sample. So when it was first measured is going to be the vertical intercept. And we can see that vertical intercept is directly on that line that says 2,000. So because it is directly on the line and that line is labeled, here we can make that statement that it was 2,000 milligrams when it was first measured, because it is directly on the labeled line. So we do know for certain. And choice E says after 4 hours, there were 100 milligrams of the chemical in the water. And so they're talking about this point down here at the bottom. And while we know it's somewhere between 0 and 400, and that could conceivably be 100. We don't know for sure, because when we originally estimated that it might have been getting cut in half each time, 2,000, 1,000, 500, 250, we originally would have been assuming that it was 125. So we could try to assume that it was 125 in the beginning, or we could now be assuming that it's 100 because that's what E says. But in either case, this is still just an assumption. We don't know for sure because it's not labeled and it's not on a line that is labeled. So we could not for certain know that E is correct. If you have any questions about a problem like this, about how to know when you can say that you know the number and when you can't say for certain that you know the number, leave a comment below and I'll get back to you with any clarification I can offer on this. Our last practice problem says the graph shows the amount of a chemical in a patient's body at different times measured in hours since the levels were first checked. Could the amount of this chemical in the patient be decaying exponentially? Explain how you know. So we have a graph with 3 of the points labeled. So we can check to see if those first 3 points are decaying exponentially, but we won't know for sure if all of them are because we don't have the actual points labeled on the rest of them. So let's check the first point and the second point. We have 600 as the y value for the second point, and we have 1,000 as the y value for the first point. Right here and right here. Well, we can simplify this by dividing the top and the bottom by 200 each. 600 divided by 200 becomes 3, and 1,000 divided by 200 becomes 5. So this means that from the first point to the second point, the growth factor would be 3/5. Now we need to compare that to the growth factor from the second point to the third point. So here we have 360 and 600. So 360 divided by 600, and both of these numbers are divisible by 120. So 360 divided by 120 is 3, and 600 divided by 120 is 5. So again, the growth factor between the first and second point was 3/5, and the growth factor between the second point and the third point was 3/5. So because these two match, we would say, yes, it could be decaying exponentially we don't know for certain because the rest of the points aren't labeled. If you have any questions about how to solve any of the practice problems from Lesson 5, please leave a comment below and I'll get back to you with any clarification that I can offer you. Now let's go and take a look at our learning targets and make sure we're comfortable saying all of them. Here are the 3 learning targets that we had for this lesson. Number 1, I can explain the meanings of A and B in an equation that represents exponential decay and is written as y equals A times B to the power of x. So I hope that after those practice problems, you understand that in this format, A represents the initial amount, B represents the growth factor, the number you're going to multiply by each time, and X represents the input. That's telling you how many times you're going to multiply by the growth factor. Learning target number 2. I can find a growth factor from a graph and write an equation to represent exponential decay. I hope you understand that to find the growth factor from a graph, you're going to take the second y value and divide it by the first y value. Then all you have to do to write the function, remember that A is the initial amount, which can be found on your vertical intercept, times B, which is your growth factor. So once you find it, you can plug it in for B. And then X is going to be your input. So you're going to make that the exponent. And learning target number 3, I can graph equations that represent quantities that change by a growth factor between 0 and 1. I hope you're able to take the values for your input and your output after you multiply by that growth factor repeatedly, and then plot those points on the graph to represent your exponential decay. If you feel comfortable with all 3 of these statements, then you're exactly where you should be. If you still have questions about any of these 3 learning targets, please leave a comment below and I'll get back to you with any clarification I can offer. If you found this video helpful, please take a moment, hit the subscribe button, give this video a thumbs up, and please comment and engage with me. I appreciate you taking the time to watch this. I look forward to seeing you in the next lesson.